Sir has published several articles in reputed journals and conferences, and sir is also implementing several projects funded by government agencies. So this now I request Ratnagar sir to please start the session. Sir, please unmute your mic, sir.
Okay, thank you, Deepak, for the introduction. So let me start. I'm sharing that my screen. Just acknowledge whether you are able to see the screen or
Yes,
not.
sir.
Is it visible? Your
Yes, sir. Yes, sir. Now it is visible, sir. Visible.
now
Sir.
visible? Okay. 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 So let us start the session on spatial and frequency domain filtering. So this particular topic is, though this is a old topic, however, many advancements have been made in this direction. Now has been widely used in deep learning neural network for several applications. So in order to understand the recent advances of this particular filtering in different areas, we need to understand the fundamentals. So there are two basic ways how we apply filters into different signals and images. So we can get the details of the signal, some properties or features from the signal using filtering. So let us start by answering the question why we require filtering. So why we use filtering in different applications. So the answer is to capture the desired properties or features in an image or any signal. So what we do to process any data that might be a signal, 1D signal or a image or a video for analysis for different applications, we need to acquire some of the properties and features which are inherent in the particular object or inside an image or a signal. So to capture those properties, we require some kind of processing. So those processing can be considered as a filtering. So one of the application could be sometimes we want to signal image quality to be improved. So quality improvement is one of the critical aspect in many of the applications. Image restoration from degraded observation. So this is also an important aspect when you try to process any image or video. So we have to capture the data is captured and different diverse environments. So during this image capturing, sometimes it may happen that images are not in a good condition. So there are several artifacts that might be present. So before processing or getting some desired features from the image, from using some filters, different filters, we need to restore the image from the degraded version. So that restoration also requires kind of filtering. Then to remove the undesired components such as noise from any signal. So which is I told that image restoration can be from noise as well. There are some undesired components that might be present. Though the image quality or signal quality may be high, however, there are some noise that might be present in any signal or image. So that has to be removed. So for all these requirements, and further processing an image or signal for different application, we require filtering the image either in the original domain, which we call as the spatial domain for reference to an image. Also we can convert the image or signal into a different domain known as frequency domain, where we apply filtering. So we'll see right now what are the how the image and signals are filtered in spatial and frequency domain. What are the pros and cons of each type of filtering, and which one should we use at what point? So nowadays the trend has been is changing. Now people do not constrain themselves to use only a single domain. Rather, they use multi-domain filtering, that is spatial as well as frequency domain filtering. So in order to design a particular filter for a specific application, we require to understand the basic fundamentals behind spatial filtering and frequency domain filtering, so that we can use those understanding to design our own filter and tune our filter so that we can capture the desired properties or exact feature which is required for the analysis. So basically, as the topic says, the filtering techniques can be utilized in spatial domain as well as in frequency domain. So spatial domain filtering mostly focuses on mask-based processing, where we use a filter mask which is applied onto the original signal. So where you have like if we try to target an image filtering, so there are some we consider the image filtering in terms of pixel processing in spatial domain filtering. So where we work with neighborhoods. So for mask processing, we generally keep the neighborhood more than 1 pixel. That means to filter a particular pixel, we also work with the neighborhood of that pixel. So the neighborhood pixels along with the original pixel to be filtered are targeted at a time. And the neighborhood size could be of 3 cross 3, 5 cross 5, 7 cross 7. So instead of acting on a single pixel, we use the mask to be applied on the whole neighborhood pixels. So the transformation function which is used is in the form of a mask. So the kind of filtering that the output that we want at the after the filtering depends on the what mask values we use for filtering. So now this is the typical filtering process using mask processing. Here you can see that like if an image is represented by a matrix of some size, suppose m cross n, and we try to target filtering of the pixel positioned at xy, so we can use this neighborhood pixel mask, like 3 cross 3 mask is shown here. So you can see that there are different weights that are used at the mask, that is w minus 1 minus 1 minus, so this minus 1 minus 1 minus 1 0 indicates the neighborhood of that particular pixel. So which is now currently if you target w00 at the position the pixel at 00, you also have to apply the mask on its neighborhood. So if we use a 3 cross 3 mask, so we need to go beyond 1 pixel to the left, 1 pixel to the top and bottom, and so on. Now mathematically, that filtered output for that particular pixel, if f of xy, the input pixel g of xy, could be written in the summation equation. That is a basic equation for filtering, which says that using a particular mask of w, so we have summation over I equal to minus 1 to 1, j equal to minus, so minus 1 to 1 represents the neighborhood pixel. That means if you are targeting 00, we need to go back to the 1 pixel left and 1 pixel right. But in general, in particular application, if you start with 00, so there is no pixel that are present with from at minus 1 and minus 1 position of the left position of that. So in order to apply the filtering at position 00, we may extend that matrix by 1 pixel to the left, 1 pixel to the top and bottom, and so that's the kind of processing that we do with the mask. So if you use a particular mask, the mask values will be multiplied to each of these pixel values, which are known as gray values, and they are summed together. That's known as a weighted sum. So in order to generate the pixel gxy, now fxy is the original pixel value or original signal value, which after filtering it generates gxy using a filter mask w. So mask processing techniques can be of different types. We can, as I told, that the values in the mask decide what kind of filtering we are targeting. So the different mask types generates different types of filtering. We can have linear smoothing, or also known as linear filtering. We can have median filtering. So these slides are mostly targeting towards the image filtering concepts, because if you are able to understand how to filter an image, so that is more common in applications like deep learning, which has been targeted for image recognition problem. So now same thing also can be applied in one dimension as well as extended to three dimensions very easily. So linear smoothing and linear filtering, then median filtering and Sharpen filtering. So now let us see how this filter works, and how it helps in getting the required features from an image. So there is in case of linear smoothing, also known as image averaging, we can replace the intensity value of the pixel with the average of the intensity values of its neighborhood. So as I told that when you work on a particular pixel, we use a filter mask, and mask may be of 3x3 size. And if the mask values are kept as one, and the whole total value is divided by the total number of cells in the particular window. So as the window is size of 3x3, we can divide that whole window by whole value by 9. So that gives a image averaging operation. That means the window where it is applied onto the particular image area. So those values are added together and divided by the 9. That means output value is just the average of all the pixels of its neighborhood. So in an area of 3x3. So if we do that, so that filtering output smoothens the particular image and gives a blurring kind of effect. So now it says that output image is a smooth image and sharp edges are blurred. That means when you try to apply this particular mask onto a image, so each value like 1 1 1, all these are they're multiplied with the pixel values at the corresponding position, and they are all that is same as equivalent as averaging all the pixels within a neighborhood of 3x3 and divide the whole pixel values by 9. So by doing so, we get the sharp edges blurred, and blurring will be more if mark size is getting bigger and bigger. So sometimes what happens, as I told that noise removal is one of the basic operation that we do in every image and video processing. So in order to remove noise, which are sharp intensity values abruptly present inside the image. So in order to target those sharp intensity values, we could do a mask-based processing, which is the smoothing operation, which is nothing but a image averaging operation. So when you go on, if we have the noise intensity more and more, we can enlarge the mark size from 3x3 to 5x5, 7x5 based on the requirements. And I can just see some results. So those results have been taken from the image processing book. Uh, so image averaging operation, you can see the original image, then using 3x3 averaging masks which are applied to the whole image. So you can see the blurring effect that appears onto the image. And when the mask size are increased to 5x5, the amount of blurring increases. It increases further by using the mask of 9x9. So sometimes this linear smoothing is also useful to remove the noise from the image, and being used for remove the blurs, or remove the edges which are not unwanted edges from the particular image, and can be used for many applications. Now, so the previous example which I have shown was the example of simple averaging operation. So later on, these people thought that why to make the simple averaging operation. So they have developed a technique of weighted averaging operation, where these mass weights are some of the weights are attached to in each value of the mass. That means instead of taking all the values as one, we could do better by keeping the central value as more strength by and assigning more weight to the central value, and when you go outside the center, the mask value decreases. That means you can see a corresponding mask is shown here: 1 2 1 2 4 2 and 1 2 1. So it in this weighted averaging, what it does, it simply multiply the weights and each value, each mask value correct to the corresponding pixel value, and the operation remains same. Only the change in the mask values. If the mask value changes, the importance of each pixel and the output also changes. That means based on the weight value, the output is produced. So blur will somehow reduce as compared to the simple averaging. When you do simple averaging, all pixel values are weighted equally, that is by 1. So when you apply the equal weight, the average blur, the amount of blur is more. So instead of doing that, if you want to remove from a noise or any sharp value from a particular image at a particular location, means we can apply this weighted averaging concept. So the weights depends on type of noise that you deal with, and the amount of noise that we deal with. So depending on the amount of noise and depending on the application, we can set our weights in the mask so that weighted averaging will suit to the corresponding output. Now same operation, weighted average operation on the similar image, same image. You can see the 3x3 marks, simple averaging and weighted average. So might not be possible to just know the effect from the image itself, but when you quantify these blurring effects on the image, you can easily know that the blurring effect is less in weighted averaging than your simple averaging. Now coming to median filtering, so these are the fundamental filtering approaches used in image processing. So we need to understand these basic concepts. Then only we'll be able to apply or design our own filter for complex filtering in deep learning and CNN based models. So now coming to median filtering. So median filtering is a kind of approach mostly used to reduce the noise, or like one of the important noise is Sultan paper and random valid impulse noise. So that is inherent in the many image capturing applications. So to deal with those kind of noise, so we basically use median filtering. So it's a order statistic filter and it's a nonlinear filter. So it reduces salt and pepper noise. So salt and pepper noise is kind of a noise. That means in a particular image, if some due to some effect, abrupt value of 255, if you keep the gray values, consider the gray values from 0 to 255 in a 8-bit grayscale image. So sometimes what happens in an image, some abrupt gray values may change to 255 or may change to 0. So those abrupt gray values can be considered as salt and pepper noise. So in order to remove those noise, this median filtering approach has been seen to be very efficient. And so this approach, what it says, in the particular mask, it uses a mask of size, let us suppose 3x3. So it sorts the pixels in a ascending order, as you can see from this example. So this 3x3 patch of a particular image containing different values 185, 98, 99, and so on. So we try to filter out the values 95. So is the target value. So what we can do, we can simply consider all these in a ascending, or sort these neighboring pixels in ascending order, and keep the replacement the median value of all. So you can see that the 95 has been changed as the median value of that. So by changing this from the original value to the median value, we'll be able to reduce the salt and pepper noise effectively. So as well as we can, if so this is an example of actually random valued impulse noise. So which is a subset of, we can say that salt and pepper noise is a subset of that. Salt and pepper is now 0 and 255. However, pepper is because pepper noise is 0 and salt noise is 1 or 255. So in order to target those values, we can use this median filtering. So here example of random valued impulse noise is shown, where this 95 value has been replaced with the median of the neighborhood. So the median of the neighborhood comes to be 99, and 95 has been replaced with 99. So this type of median filter is very much suitable for reducing noise in an image. You can see that so this noise is measured mostly in percentage. That means almost all the pixels are not affected by this noise. So we measure some of the pixels which are affected by, or some of the pixels which are replaced abruptly by salt and pepper or random valued impulse noise. So we can measure that in percentage. So this same coin image with 20% of the salt and pepper noise has been shown. So now you can see that using 3 cross 3 median filter. So this 3 cross 3 median filter, in the sense we use a 3 cross 3 mask, and the mask is being moved from top button. So you can start with the filtering process by keeping the mask at the top corner, top left corner, and moving the pixel from top left to right bottom. So by moving and filtering, and each pixel, noisy pixel, has been replaced by the median value, you can see that 3 cross 3 median filter has almost reduced the noise, and still there are some amount of noise present. So those noise also can be further reduced by using a 5 cross 5 median. However, the consequent of that, using higher mask, as you have seen in the previous slides, that it increases the blurring effect. So that's a that means, though we are able to reduce the noise fully from the image, but we are able to get we are getting the blurring effect on the net output image. So in order to reduce the blurring effect, one, we need to reduce the mask size. However, you can you have to tolerate, or we have to be uh, specific about how much noise percentage is there. Accordingly, we should use our mask, so that we will be able to have some noise without having blurring effect. Now, the previous filters, weighted averaging, median filtering, or averaging, simple averaging, so they are mostly used to smooth out the image, and it's a kind of smoothing operation. So smoothing operation is generally used to remove the noise. So there is opposite kind of effect that is also used in many image processing and signal processing applications. So by filtering a particular image or signal, we can sharpen some of the properties. So sharpness, in order to increase the sharpness of the image, we can use some of the mass processing techniques, which can be known as sharpen filtering. So here the objective is to highlight the intensity details. So in the previous case, we are by trying to repress or suppress the undesired effects or noise which are present during due to some environmental or capturing conditions. So we have used the smoothing filter. So in that case, we get the blurring. However, in some cases, we require to highlight some of the features or intensity and the image, intensity details of the image. So those intensity details are used for further analyzing the image. So in order to get those filtering, we can use this kind of filtering known as sharpen filtering. As the name suggests, we need to sharp the image, sharp is certain properties of the image. So sharpening is achieved by using operators like derivative or differentiation operator, so which generally increases the sharpness of the image. So first order and second order derivative operators are used for this purpose. So derivative in the with respect to, as we know, that differentiation operation in a discrete signal can be achieved by making the by taking the difference of the particular value from its previous value, or from its previous value, and from the so that we can get the difference of the values from its neighborhood. So that may give a kind of derivative or differentiating effect. So that is usually done for certain filtering. So we can do the differentiation or difference in different orders. So first order and second order derivatives are more popular for popular in sharpen filtering approach. So for first order derivative filter, you can see that must be zero in areas of constant gray level, and as you say, the second order derivative filter zero in flat areas. First order derivative filters are non-zero at the onset. So we'll see that how this first order and second order derivative filters work to sharpen an image. So this is the basic difference. So let us directly go to the equations, how, so that we can understand better. We can know that so to understand the differentiation concept for the discrete signals. So as we know that differentiation for continuous signal can be defined like is a basic mathematical equation for differentiation. So derivative in discrete domain, as I told, it's the difference of the pixels for first order. If you want to go for another order, so we can add the two neighborhood pixels of f of x, that is denoted by f x plus 1 and f x minus 1. So that is written for in a particular dimension. So if you have a two dimension, similar thing can be extended to two dimension as well, like x plus 1 and y plus 1. So that also is shown here in the next slide. So for second order differentiation, we need to add the two values, two neighboring values, f of x plus 1, x minus 1, and take the difference and from minus to f of x. So the signal value multiplied by twice is uh, taken difference from the addition of the neighborhood value. So that will give a second order derivative effect. Now, same thing has been shown here in 1D signal example for how to apply Sharpen filtering for a 1D signal. So you can see that first row shows the values corresponding amplitude values, and the f prime or single first order derivative will be the difference of the signal from the neighboring pixels. So for the first one, it is 0 because 5 minus 5 is 0, 4 minus 5 is minus 1, and so on. You can see this, so that will give a effect of first order difference. So when you try to take the second order difference, so this is further differentiated by the similar operation. That means f double prime could be achieved by minus 1, minus 0, minus 1, minus 1, and so on. So you can see that same thing in the when you try to plot those signal in the in a plot, you can see that the plot how the 1D signal and corresponding differences are shown or look like. Now first order, so what are the observations? Why you go for differentiation for sharpening or sharpening filtering? It is observed that first order derivative generally produces thicker edges. So second order derivative, you go on more stronger response to get the fine details. So mostly we use the second order differentiation filter for or sharpening filter, we can say, to get the more fine details than such as thin lines and isolated points. So which are very much useful in identifying the smaller edges. And first order derivative has stronger response to gray level step, whereas second order derivative produces a double response at a step edges. When there is an edge at a particular step, so this we need to find out the second order derivative so that thus edges can be more prominent. So you can conclude that second order derivative is always better suited for image enhancement and image quality improvement. Because suppose somebody wants to increase the sharpness in a particular image and edges and highlight some of the objects or some of the pixels, so we should go for second order derivative filter. So this the whatever filter that I have shown, first order, secondary order derivative, that's a simple difference. So one of the widely used second order derivative filter is the Laplacian filter, which is mostly used for sharpening images. So this Laplacian filter uses gradient operation. So in order to filter a particular image, so you can see that the formulation of a Laplacian filter can be defined by this equation. So del square f, so which is nothing but the gradient of second order difference in a particular direction. So with respect, so f is the original signal. So if we try to find the Laplacian for the particular function, so we take the second order differentiation in the x direction and y direction and adding them. So that is the for the continuous domain. So if you try to write the similar equation for discrete domain, it could be like f of x plus 1 y plus f of x minus 1 y. So that is like if you have to take f of x y is the central pixel, we take the x plus 1 and x minus 1, so the neighborhood pixels in the right and left, and add their values and subtract it from twice the value of f of x y. So that is same as the second order difference in x direction. Similarly, second order difference in y direction can be uh, can be obtained by taking the neighborhood pixels in the vertical domain, that x is kept constant, and we take the neighborhood of, that means we are trying to get the difference in the in the horizontal and vertical domains by taking neighborhood in horizontal and vertically. So whenever we want to sort the edges in a vertical and horizontal direction, so we can take the second order difference like this using this equation. So by combining these two, this Laplacian can be formed. So you can see we can add those two values of differences in x direction and y direction, that is same as second order derivative in both the direction. You can see the f of x plus 1 y, f x minus 1 y, x y plus 1 x y minus 1 minus 4x. So considering this operation as the Laplacian operator, so this is a Laplacian operator. So how to write a corresponding mass, because we have understood how to process the mass to create a filter. So this similar mass can be created. So those are known as Laplacian mass. You can see that the diagonal values are kept as 0, and x plus 1, x minus 1 are weighted with the values 1, and the f of xy, which is the central pixel, is weighted by minus 4. So by doing that, we will be able to get the difference of the pixel from its vertical and horizontal neighborhood. So that will that can highlight the edges, sharp edges in the horizontal and vertical direction. So instead of doing that, so like other mass, similar mass also can be created to highlight the horizontal and vertical diagonal lines by keeping all the values as 1 and central value is minus. So a summation of all the values, so negative of that could be placed in the center. So that means if I keep 2, 2, 2 in the diagonal and horizontal values, horizontal and vertical values, the central value could be minus 60. So in that way, we can keep all these values as one difference from the central pixel to the other neighborhood. So you can see the similar mass also can be created. So all those mass are known as Laplacian mass, so which are most popular for highlighting the edges in the vertical and horizontal direction as well as diagonal lines. Now you can see, so one of the example of a Laplacian filter in the corresponding image, you can see that. So the first image is a somewhat blurred version of the moon image. Some blurred version of the moon image, if you try to apply Laplacian operator on that, so we will be able to enhance the particular image or sharpen. They can see the many of the portions or many of the pixels which are blurred are very much prominent and clear in the output image using Laplacian operator. That means whenever depending on the requirement, we can go for smoothing operation as well as sharpening operation using different filter masks. That means filter masks are put on the or placed on the particular image or signal, and we try to take the weighted combination of the weights. So the weights are very important. So when you go on changing the weights, you will be able to get your different properties and different objects and different pixels which can, or intensity values you want to highlight, could be utilized or obtained at the output. So that purely depends on what mask you use and what operations you are uh, going to do. Now coming to frequency domain filter. So this special domain filter, we mostly work on the signal values or image values directly, whether it is signal, image or video. So you can try out different masks for different operations like smoothing and sharpening, and apply these mask operations onto the image or pixel directly. So instead of doing that, so there is another way of filtering the image values, image and video signal. So that approach we can tell as the frequency domain filtering approach. So this frequency domain filtering approach is little different from the spatial domain, so where we do not use any mask. So the current deep learning approaches in CNN, say different CNN layers, we use some filters and filter masks. Like we have seen that we the different layers, we use different filters. So that are examples of purely the spatial domain filtering. So nowadays, the spatial domain filtering has been changed to frequency domain filtering. Though they are the basic operations were quite produced quite well for many of the applications. So now they are combined. They are also being implemented in on the deep learning based models. So where this all the operations are carried out in frequency domain, so using some kind of transfer functions or filters. So the filter or filter mask which we have seen in the spatial domain, so those are considered in considered as also the filter and transfer function, but filters. However, when you talk about frequency domain, we just slightly term them. We can term them as transfer function. That means spatial mask for special level filtering HXY can be converted to corresponding transfer function HUB. That means the same theorem, same similar concept are being used. Means we suppose if you are able to use a sharpening mask for in order to highlight the intensity and edges of a particular image, same filtering operation can also be easily carried out in using a transfer function HUB. So HUB is the frequency domain equivalent of HFXY. So now mathematically, if you see how this looks like that, like you can see, so there are different filters we use in the frequency domain. So let us try to understand the basic operation, then we'll come back here. So now any filtering process and frequency domain, we can mathematically express as GUB equal to HUB into FUB. So let me just take some time to describe this particular equation. Like we have seen that the filtered output image in spatial domain filtering, G of XY is the F of XY. So F of XY convoluted with H of XY, where H of XY is the filter mass. So that gives a weighted sum operation. So that is same as our convolution, most popularly known as convolution operation. So in order to get filtering for a particular image or signal, we need to convolute, we need to apply the convolution operation of the particular mask onto the image. So instead of applying the mask onto the whole image, so convolution is done on a window by window basis. So what we do, we take the mask on a window on a particular area of the image and try to get the features out of that. So that is same as your convolution operation. So there is a very good property that exists in convolution. So that says that when you apply convolution operation in spatial domain, so that same operation can be achieved in frequency domain with a simple multiplication. So if I replace this equation, g of xy equal to, so all are in all notations could be small. So g xy are small in given in small caps. So I can write g of xy equal to small h of xy convolution with f of xy. So h of xy is the mask, f of xy is the image to be filtered. So the same operation, if I try to convert or write in frequency domain, so that becomes multiplication. So as you know that mathematically multiplication operation is very simpler than the complex convolution operation. However, so we have to convert all those values like your f of xy and hxy into their corresponding frequency bands. That means we need to apply the Fourier transform. So this useful transformation that is mostly used for filtering and getting the frequency component of a signal. So for using the Fourier transformation tool or technique, we can convert each of these values like h of xy, which is the mask, f of xy, which is the image, into their corresponding frequency based representation. So as you can see, FUV is the transfer is the Fourier transform of the original spatial image, HUV is the transfer function, and GUV is the enhanced image in the frequency domain. Then finally the image, we require some the image GFXY. So GUV as we have obtained GUV from the multiplication. So this multiplication is not a matrix multiplication, as you see the square bracket, the parentheses that are shown shows that they are multiplied in a element wise, because for different values of UV, FUV and HUV are multiplied, so which generates GUV. That means so HUB has the same size as FUB, because but that is not same in your convolution process. Convolution, we generally use h of xy as a window function or mask, which is of very smaller size than the corresponding image or signal. So what we need to do in order to convert, before converting into the frequency domain, what we can do, hxy has to be increased, the size of hxy has to increase to the size of f of xy, which is the size of the original signal or image, which is in the spatial domain. So once we increase the size and get the similar size as the original image, then we take the Fourier transform to in order to convert into HUV. Now, once we make HUV and FU as of similar size, so you can easily multiply them in order to get the transformed image multiplied with the your filtering function or transfer function. So in this case, we call that the transfer function. So in order to get the special version of the output, because finally the whatever the GUV that is obtained after the multiplication is not the original image to be recovered or original image to be produced. So we need to again convert them back into the spatial domain by doing inverse Fourier transform. So here you can see GXY is the F inverse of GUV. Now I think same thing has been shown here pictorially for better understanding. You can see, so f of xy is the original image. We because it's set in 2 dimensions, we can use 2-dimensional fast Fourier transform, which is an algorithm used for computing the Fourier transform of an image. Then which gives you FUV, and you have problem specific HUV. What is problem specific? Because we have seen in the special domain, so there could be smoothing filter, there could be sharpening filter, and other filters as well as weighted averaging. Likewise, depending on the specific problem that we try to address or try to obtain the feature, we can design our own filter of filter mask. So those filter masks is extended to the image size and converted into its corresponding frequency domain. Then after getting the multiplication GUV, that is the element wise multiplication, so we can take the inverse Fourier transform. So that is again 2D IFFT. So IFFT is also the algorithm for finding inverse Fourier transform, which will finally generate the GXY. So this filtering process is we carry out the filtering process in the frequency domain. That's why it is known as frequency domain filtering. So that has the several advantages over special domain. So here, if we try to highlight a particular region specific or particular frequency band, like for some of the application like synthetic aperture radar application or the remote sensing operations, remote sensing image application. So we may have to highlight some of the properties of the image in a different frequency band. So that is very crucial for different applications. So in order to highlight a particular frequency band, it is always better, it is always advised to convert the whole image into corresponding frequency representation, so that we can know which frequency bands are present, which can be highlighted very easily. So we can use this filtering process in the frequency domain so that we can identify and highlight the corresponding frequency band. So this frequency based application or frequency domain filtering process is very essential. So there are, as we know from the common filtering process, there are different kinds of filtering, like depending on the frequency band you want to highlight, the filtering types are classified into different types, like low pass filtering, high pass filtering, band pass filtering. So let us see some of the filterings in the filters in the frequency domain. So here you can see, so that's a the diagram shows that the frequency response of a particular filter, so that is a low pass filter in frequency domain. So it looks like a Gaussian filter, like a Gaussian shape, where you can see that after a certain band from the left and right, the frequency response reduces to 0. So that depends on the what kind of spatial domain filtering you use in the spatial domain. As we've seen, one is shown as the simple averaging mass, another one shown is the weighted averaging mass. So depending on the type of mass you're filtering or low pass filters, so they are known as low pass filter. That means after a certain frequency band, we need to reduce or make the cutoff of frequency so that we can suppress the high frequency signals That means you want to smooth out the transitions, sharp transitions, which might be a noise in case of smooth and filtering. Similarly, corresponding high pass filter, which is the opposite of the low pass filter, you can see. So here we try to um, suppress the low frequency counterpart, low frequency signals, and try to highlight the high frequency bands. So after a certain, up to certain frequency U, which HU response is 0, and after that we try to increase the frequency response, means the filtering output response increases after a cutoff frequency. So same thing is shown in the special version. You can see that we have seen that sharpening filter. So high frequency, high pass filter in the frequency domain can be same as it can be thought of as a high pass filter in special domain, or sharpen filter in the special domain. We have seen the sharpening mask. So this sharpening mask look like this function of h of x in the special domain and corresponding frequency domain. Now you can see the effect of this low pass filtering and high pass filtering onto a particular image. So as I have told, that you can see that Gaussian like shape, and which have frequency components u and v after a certain range for some values, specific values of u and v, the response becomes 0. So that makes the effect of blurring. That is same as your your smooth filtering in spatial domain. Corresponding high pass filter, which is exactly the opposite of low pass filter, also known as sharpening filter in frequency domain. So you can see we are able to highlight the edges in the particular image, and low frequency components, like which the uniform portions are considered as outputted as 0, and other values are highlighted, sharp frequencies are highlighted. So this is the operation that we carry out in the frequency domain. Now frequency domain filters, as I have told, image can be enhanced in frequency domain using smoothing and sharpening. So smoothing is used for the same reason as we have already discussed. Smoothing is used to reduce the noise within an image based on the low pass filter. Similarly, sharpening is to highlight the contrast between bright and dark region, or highlight the changes in the image, sharp changes in the image. So this is very important to bring out the edges and specific features which might not be present in the original image but not highlighted properly. So we can use a sharpening filter in the frequency domain that are known as high pass filter, and it is basically the application of high pass filter to an image. Now we can discuss if we have the low pass and high pass filter versions. There are there are the ideal cases as well. So in case of ideal case, we should have a sharp transition from your low pass to high pass. You can see that whenever for a particular up to certain frequency, it gives a equal response if DUV is less than equal to D0, so the D0 can be considered the cutoff frequency, and HUV is the corresponding transfer functions which is being multiplied. That means when you try to use an ideal low pass filter, so after a certain cutoff frequency, so the image values will be completely made 0, and other values are kept intact for up to certain cutoff frequency, that is 1. That means 1 is multiplied to the your corresponding GUV or sorry FFUV function. So FFUV is the corresponding frequency version of the FFT or Fourier transform of the original image or signal. So in this way, you can define ideal low pass filter and as well as ideal high pass filter. You can see the corresponding versions shown in 2D and 1D. You can see after this a rectangular shape in 1D, and which is again a circle shape for a 2D case. So that circle denotes that apart from that radius D0, so other frequencies are considered to be 0. So low pass filter version again produces smooth image or blurred image, and this is the original image. So similarly, the results are shown for another image with different cutoff frequencies. You can see original image with cutoff frequency very small. That means we are trying to suppress all the frequencies with radius more than equal to 5. So radius is nothing but the radius of the circle which denotes the cutoff frequency. So as you can observe, the larger the cutoff frequency, the more details are preserved. So with different radius, the results are shown for the filtering. So you can see when we use a cutoff frequency or radius of 230, you are able to preserve almost all the information that is present in the image. So there are different versions of low pass, and like we have seen that different versions of um, uh, averaging filter, like weighted averaging filter, Gaussian filter. Similarly, we have different versions developed by different scientists. As per their name, the different filters are present in the literature. One of them is Butterworth low pass filter. So Butterworth low pass filter, this allows the part of the energy spectrum with higher frequencies, so to be more smoothing, like the cutoff frequency from the transition band from pass band to stop band is very smooth. So rather than a just sharp cutoff, so this produces better results in ideal low pass filter. So you can see here the corresponding frequency response is shown with the 2n is the order of that filter. So n is the n 2n power that shows the order of the filter, and d0 is the cutoff, and du the distance between point UV and center of the frequency rectangle. So you can see the corresponding image version of the filter doesn't have sharp discontinuity. Like there is a smooth transition from the pass band, like the circle, white circle shows the the cutoff frequency range. So that range is not sharply changed from white to black. So there is a smooth transition from white to black. That means it shows that the change of high frequency to low frequency is very smooth, or we are able to smooth out the sharp discontinuities which might be available in the, because this the objective of low pass filter is to just to smooth out the image, so smoothing should not be so sharp. So if smoothing is very ideal, so we may lose most of the information. So that's why this water low pass filter has been utilized in many of the applications and is a better form than ideal low pass filter. So corresponding results for water low pass filter are also shown. So all these results uh, are available in the Gonzalez book, so which I have taken while teaching all these filtering process into our students. So you can see that the larger the cutoff frequencies, the more details are preserved. Like and you can, if you measure the quantitative response of this particular filter, so you'll get better response than our corresponding ideal low pass filter. Similarly, another versions of low pass filter is the Gaussian low pass filter. So Gaussian low pass filter has a response like this. So you can see the smoothing is more in Gaussian than corresponding Butterworth. So several improvements have been made to this kind of filters. So these are the fundamental filters when these filters are developed in frequency domain. So this long back these filters have been developed and has been improved a lot nowadays. And there are different combination of filters, Gaussian and Butterworth, and all ideal filters are being used nowadays. So you can see the mm, different pictures that show the how this frequency response changes with respect to the different values of d naught, that is the cutoff frequency, d naught 10, 20, 40, 100. You can see the smoothness in the transition from pass band to the stop band. So the portion which is being passed to the output are known as pass band, and after cut off, the values which are suppressed in the stop band. So we generally give these terms in filtering. So results of Gaussian low pass filter, you can see. So from these particular images, we are may not be able to identify what is the better what how this particular filter is better than ideal and all this case. So we can always measure this quantitative performance in the image output to in order to show its efficiency in terms of the output response. Now similarly, same thing can be extended to high pass as well. High pass is the just the reverse of low pass, where you can say that HUB equal to 0 for a frequency less than D0, and other values are kept as it is by multiplying the values with 1 or unit value. So similar functions are possible for ideal. You can see that sharp transition from black to white. In case of low pass, we are having a transition from white to black. Here it is from black to white because it's a high pass filter. Corresponding frequency response plot is shown in the left side. You can see that the middle image is the middle plot is the image version of the corresponding filter, and the functional form is shown as a rectangular. You can see that there is sharp cutoff after a certain frequency. The values are 1, other values are 0. So if you use this ideal high pass filter, corresponding Butterworth high pass filter, and uh, the corresponding response, so you can see the smooth transitions from black to white, and corresponding um, response in the functional form as well as the plot form. You can see HUV, it is a smooth transition. So smooth transition is more clearly visible in the image format. So it doesn't have a sharp cutoff and make the filter to allow a part of the energy spectrum at lower frequencies. So this is the operation of high pass filtering for a X-ray image. You can see it is able to highlight the edges, some of the persons which might be useful for further analysis and might be useful for identifying the disease. Gaussian version of high pass filter. So here you can see that D0 is the spread factor, and this gives a response like this frequency filter. So this filter is more smoother. Visible from the functional form in the plot. You can see. Now the results, some of the results for applying Gaussian high pass filtering on the same image, which has been shown for other filtering approaches. Of this is of order 2. So for different cutoff frequencies, you see that how we are able to get the output image, output Gaussian filtering image. So when a cutoff frequency is low, so it's somewhat blurring, and it increases when the frequency increases. We are able to get the high frequency component.
Sir, your screen is not visible, sir.
Screen not visible.
Not, sir.
Why? Oh, okay. Click share to content. I think there was some. I'm again sharing.
Sir, you can reshare, sir. Yes, sir.
Okay. Is it visible now?
Now it's visible, sir. Now.
So
Yes,
from
sir.
which slide it was not visible?
I think, sir, the previous slide.
Previous slide. Okay. So I was talking about the different kinds of Gaussian filtering, high pass and low pass filtering. As you can see that this Gaussian filtering is more smoother, having smooth transition from the stop band to the pass band. So as per the requirement, we can adjust the frequency factor so that we can have the transition from pass band and the required frequency band to be highlighted in the output. So this is the result for the same image of with different cutoff frequencies. Now, combining low pass and high pass, we can have a band pass filter which can restrict our signal from in two different frequencies like D1 and D2. So we can form a similar function like this, that HUB. So that seems to be ideal band pass filter. So instead of ideal band pass filter, we can extend easily those filters into by taking combining high pass and low pass. We can easily design a band pass filter. And we can use this band pass filter for different or identifying certain frequency ranges which might be useful for further analysis. So we have seen the different kind of filtering approach, that filtering approach we can use in spatial domain and frequency domain in order to highlight the specific portions of specific intensity ranges, specific frequency bands, which might be useful for further analysis. So though these concepts are also being extended nowadays. So whatever I discussed are more fundamental things which we should understand, must understand how the filtering is carried out. The same frequency, the same pixel based operation using mask and using convolution can be easily converted to frequency bands, and can be modified to a product function. So we can apply the similar concepts using in using for using wavelet filters and other filters. So many filters have been designed in frequency and spatial domain and being used for many for identifying different properties. So all those filters have used these basic concepts of frequency domain and spatial domain filtering, and they try to highlight for some specific part, like spatial some of the cases spatial information is important, some of the cases frequency information important. So they try to use combination of spatial and frequency domain based filter for their applications. So here I can conclude that we have several research directions in this domain. So we can design hybrid spatial frequency architectures which are dominant trained. So they can combine these local and global cues and are providing superior across restoration, classification, and generation tasks. So we can have trainable frequency models, like nowadays learnable FFT and wavelet filters are being used, and we use attention mechanisms to after filtering the certain areas, but for a better adaptability, and then classical fixed filters. So which I have discussed are classical fixed filters. So we can always use that in a learning manner. That means this filter weights or filter marks can be learned using different optimization algorithms, so that these filter marks will be adaptive at different regions. So suppose you have we need to have different masks at different regions, like we use in CNN and other deep learning based models. So if we are able to learn those filters which can be suitable for different areas, and can identify specific regions and specific properties of a particular signal or image at different regions, so those could be useful. That can be achievable using trainable frequency models. That they can be increasingly integrated into mainstream deep models. There are application specific frequency technique like which we use in hyperspectral imaging, synthetic aperture radar image. So mostly we use this specific frequency domain filtering in this remote sensing applications, hyperspectral applications, as well as in medical imaging, where frequency band information is more important, and we try to highlight some of the frequency region, how the corresponding disease appears in different frequency band, and the diseases are more prominent in a particular frequency band. We try to highlight those frequency bands. So those are possible in using these frequency domain filtering techniques. And most of the cases we try to use always nowadays, almost all literatures talk about the hybrid spatial and frequency domain architectures, which are useful to obtain global and local information from the image, which combiningly can be used for further analysis and can be used for uh, analyzing the good properties and bad properties, and what are the useful information that are hidden inside a particular signal or an image. So here I stop because I am done. So I have mostly covered all these slides from this Gonzalez and Jane. Thank you all. So if you have any questions, because this all the other topics which I heard from Professor Deepak is that you are going to launch CNN filtering as CNN other architectures for computer vision applications. So this frequency domain filtering and special domain filtering fundamentals should definitely will help you to understand those concepts better, because all those concepts has been taken from these fundamental concepts only. Thank you all for listening patiently for last 1 hour. Here I stop. If I would like to answer any questions if you have. Any questions from any participants? Either you have not understood or have understood the board with the session with the fundamental things which are uh, old but very useful for designing new concepts. All the new concepts that are being developed uses these fundamental things only. Once you understand this, so you can also design your own filter for different applications. Thank you all. If there are no questions, I can. Somebody is writing something. View message. Wavelet filter. Yes. So you also wavelet filters are also known as the. We can use this filter as the frequency domain approach. So which try to highlight the particular image in different subbands. It's a kind of subband filtering. You can say it's a subband filtering. So we apply different wavelet filters, different wavelet coefficients to different parts of the image and analyze the image at different resolutions. Deepak, should I see the questions from the messages or what? Or somebody
Yes,
should?
sir. Yes, sir. Yes, sir. Participants cannot unmute their mic. They can only write in the chat box.
Okay, okay. They cannot unmute.
No, sir. No, sir.
Now they should be allowed to ask questions at the last, no?
Yes, sir. They are writing actually. Unfortunately, we are
Writing.
only
How do I
giving.
say? Chat box I can say? See? Where I should
Sir,
see?
there is a
Okay, okay,
there is
okay.
a
No, says, wavelet
there's an
filter.
icon actually for
Okay. Wavelet filter somebody has asked, no?
yeah. Any other questions, participants? You can write in the chat box.
If you're able to see, you please tell me, Deepak.
Yes, sir. Yes, sir. I will summarize, sir.
Okay, okay.
So I think wavelet filter you have already discussed. Session was super useful, sir. Birendra Kumar, thank you so much.
Okay.
Yes. Another question
Which
is, sir,
one is given? Which
out
one
of
is given?
frequency?
Local cues and global cues out of frequency. So mostly in spatial domain we get the local information, and global frequency
Yes.
information we use. We can obtain that using frequency domain filtering. That you are asking about?
Yes.
I think he is asking about that.
I think that's the question, sir. Yes.
Okay. So, means how to obtain local information global. Nowadays, presently,
Yes, cues. Yes, yes. Information.
local
Yes.
cues and information. So, yes.
Any other queries, participants? I hope it is clear. Sir, I want to know that what will be the
Learnable
learnable.
parameters. Learnable parameters are the filter mass. The filter weights are the nullable parameters in CNN, which you learn using the back propagation algorithm. CNN has been covered or not, Deepak? CNN?
Sir, no, sir, because after this lecture only, sir, I think tomorrow we have a lecture on
Okay.
CNN because
Okay.
before filtering and all, they may not able to understand.
Okay.
CNN.
Sir, here filters are same as what is asking. Filters are same as we use in CNN. Yes, filter mask depends on the type of application that you try to handle or deal with. Like if you want to highlight the edges, mask will be different. Highlight the or smooth out the image, that mask values will be different. So mostly CNN we use the spatial domain filtering. Like matrix, yes, it's like matrix only.
Yeah, I think, sir. Yeah, almost all the questions have been answered.
Like matrix in 2D, like if you use a signal in 1D form, so that might be a simple 1D filter. It's not a matrix. When you target to filter an image, it's a matrix. When it is a 1D signal, it's a simply 1D vector.
Yes. I think, sir, no other questions.
I
If
think
you're having
your
any
session
queries,
time is already 5:10. No,
yes, sir, yes, sir.
sir is there already joined.
No, sir.
Okay.
I think there are no other queries, sir,
Okay
from the
then. Okay.
participants.
Okay.
If you are having any queries, you can directly drop an email to sir.
Yeah.
So sir will get back to you.
Yeah.
I hope participants, you have got knowledge on filtering, which is relevant to convolutional neural network, because without filtering, you cannot able to understand convolution and all. So this lecture will be very useful for all of you. And thank you, sir, for sparing your valuable time with us and for sharing your knowledge. I know, I mean, because sir was requesting us to give some advanced topics, but unfortunately, what I found this topic is even
Actually,
more
I
important because
thought to give all
yeah,
computer vision applications in this transformer, all these things we have developed.
yes.
But
But
you,
I think this lecture is even more important because
okay, yes.
this will yeah.
Okay.
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 So thank you so much, sir. Thank you so much,
Okay.
sir, for accepting our request and delivering a talk. Thank you,
Okay.
sir.
So that Deepak, we can discuss after your sessions are over. Okay. I have to discuss.
Yes, sir. Yes, sir.
Okay. Thank you.
Thank you so much. Yeah. So participants will move on to our next session. Next session will be delivered by Professor Surya Prakash from IIT Indore. He will be delivering a talk on edge detection, relevant to again the topic which has just now discussed. It is again, you will see again edge filters which will be used to detect the edges and the boundaries of the images and videos. Right? It is again going to be a very interesting session, and followed by one hands-on session today. Please wait for 5 minutes.